The most important thing for cosmologists is precision cosmology. When I started graduate school in the mid-90s, we didn't know if the universe was 10 billion years old or 20 billion years old. Now we know it's 13.824 billion years old, and we have a precision of less than 1%. And we also have an accuracy. In other words, we've calibrated that number and removed systemic contamination from that number. It's really phenomenal. I mean, at that time, we knew of objects that were older than the universe. Supposedly, there were objects called globular clusters, and they were older than the universe. That's like finding out that you're older than your mother. I mean, it's a very bizarre situation. And quite frankly, it was embarrassing to cosmologists. Now we know it with extreme precision. With that precision comes great power. And that power allows us to assess what is the nature of this dark energy potentially. And not only that, what is it doing to our future understanding of where the universe will continue to develop in the far, far distant future. And so if the universe truly has this dark energy, chimeric form of energy, unknown, completely unlike anything we've ever had an experience with, that type of energy will eventually drive the universe potentially in a variety of different ways, none of them good. But luckily, they don't come about for tens to perhaps hundreds of billions of years. When the universe might physically rip apart, there could be aspects of space-time that at all locations develop what we call singularities, the breakdown in all the laws of physics. And certainly long before then, we will have stopped having the ability to do astronomy or cosmology. We will no longer be able to see any other galaxies after a certain point. After the universe has expanded so much, those galaxies, they'll all be redshifted so far out of observational constraints that we won't even know we live in a galaxy. We'll just think this is the entire universe. So ironically, we'll be back to the way the state of affairs was in pre-1929 planet Earth's understanding of cosmology. With the precision that I mentioned before, that we know the age of the universe, we know the expansion rate of the universe, we can do astounding things. I remember when my children turned 2 years old, you take them to the pediatrician's office and they measure their height. And basically they've got this rule of thumb based on the statistics of 100 billion people that have lived on planet Earth to date, that the child will be about twice as high, twice as tall as he or she is at age 2. So imagine if you went and you go to the pediatrician and then you come back in 10 years, 15 years, 20 years, and the kid is like 30 times bigger than that height, or 1/10 as tall. Well, you'd say, this is crazy. There's something strange going on. Your tables are all messed up. And your actual statistical sample is not a good representation of the parent population, no pun intended. So the question becomes, how accurately can you estimate how fast the universe will be expanding today versus 13 billion years ago? And there's what's called a tension, because the two numbers disagree, and they disagree by a violently unacceptable amount. The measurements that we do with the cosmic microwave background radiation suggest a universe that is billion years younger, if you like, than the universe that we see using the Type 1a supernovae. And that tension is a lot. A billion years is a big difference. That's a current problem. We don't know the Hubble constant's value. It disagrees at what's called 5 standard deviations. So there's a 1 part in several million that it could be a statistical fluke and they're both actually the same. Or it could be that the physics of the early universe that I study is very different than the physics of the late time universe that my colleagues who study supernovae study.